While studying uniform motion in one dimension, we came across terms uniform velocity and uniform acceleration. What I find is sometimes we have some difficulty in distinguishing between uniform velocity and uniform acceleration. In this video, I'm going to make an attempt to clear this misconception or this misunderstanding between these two terms, uniform velocity and uniform acceleration. Let's begin with the uniform velocity. To begin with the uniform velocity, first let us once again understand what velocity. Velocity we know is displacement upon time. That is change in position upon time. The time in which this change in position occurs. So, let us say we have we're plotting, we're tracking the movement of an object, and let us say we are making a table for that. This is time t. Let us say this is the initial position, this is the final position, and this is velocity. So at time t, let us say the initial position is 0, right? Final position and velocity will not be applicable. Right? And after 2 seconds, let's say the object moves to, it is at 0 position initially, right? And what happens is in time 2 it moves to 10 meters, right? So 0 and 10, and the velocity would be change in position, the 10 minus 0 upon 2, so it will be like at 5. And let me specify the units: meters per second, meter. This is of course second. So the velocity is 10 meters per second. Let us say in the next 2 seconds, that it means after 4 seconds from 10, initial position is 10 and it goes to 20. So the change in position is again 10 and the time taken is 2 seconds from the next 2 seconds. So again velocity will be 5 meters per second. Let us in the next 2 seconds, after 2 seconds, that means at the end of 10 seconds, initial velocity was 10, 20, the final velocity becomes, let us say, 30 seconds. So again change in position, 30 meters I meant, 30 minus 20, so 10 upon 6, that upon 2, that would give me again a velocity of 5 meters per second. So what is happening is this object is moving with constant velocity, uniform velocity. The reason is because the change in position upon time, this change in position is constant. It is 10 meters, right? 10 minus 0, 10, 20 minus 10, 10, 30 minus 20, 10. And this change of 10 is happening every time in 2 seconds. So when equal change in position occurs in equal intervals of time, we say the object is moving with uniform velocity. In other words, when it covers the same displacement in same interval of time, we say it is moving with uniform velocity. So every 2 seconds it is covering 10 meters, as you can see over here, and therefore it is moving with uniform velocity. And if I plot a graph of S versus t, right? Here we will get change in displacement, here we will get time t, right? Let us say this is 10, 20 and 30, this is 2, 4, 6 seconds. So in 2 seconds it reaches 10 meters, here it is at 0 meters. In 4 seconds, at the end of 4 seconds it is 20 meters, so here, and at the end of 6 it is at 30. So what I get is I get a straight line graph going up, right? And this is the graph of uniform velocity, the ST graph of uniform velocity, straight line going up. Okay. So this is what we mean by uniform velocity. To summarize it, when equal changes in position or equal displacement occur in equal intervals of time, we say uniform velocity. Let us now try to get a hang of what we mean by uniform acceleration. Right, uniform acceleration. Acceleration we know is v minus u upon t, that is change in velocity upon time. Here we have change in position per time, but acceleration is change in velocity per time. Right? So I'll do a similar exercise for this. Right? Let us say we have an object, and again we are making a table for this. Let us say we have time over here, right? And let us say initial velocity, final velocity. Let us say this is change in velocity and let us say this is acceleration. So let us say in 0 to 2 seconds, the initial velocity was, say, changes from 0 to, let us say, 5 meters per second. Right? So in the 2 seconds, in the first 2 seconds, the velocity changes from 0 meters per second to 5 seconds. So change in velocity is 5, and acceleration, if you know, is change in velocity per time. So 5 upon 2. So this will give me 2.5. Let me write the unit over here, meter per second square. Change in velocity will be meter per second, meter per second, meter per second, and this is seconds. And let's say in the next 2 seconds, that is between 2 seconds and 4 seconds, the initial velocity will now be 5, which was the final velocity over here. From 5, let's say it becomes 10. So the change in velocity is again 10 minus 5, 5. And this has happened in 2 seconds. So again 5 by 2, 2.5. And let us take one more. From 4 to 6 seconds, initial velocity 10, let us say the final velocity is 15. Change in velocity 15 minus 10, 5. 5 divided by 2 is 2.5. So you can see over here the acceleration is constant. Let us take one more to make the table complete. 6 to 8 seconds, 15, 25, 2.5. So acceleration is constant, 2.5 meters per second. So if I have to explain this in words, I'll say when equal change in velocity occurs in equal intervals of time, we say the object is moving with the uniform acceleration. So what is constant is change in velocity. Change in velocity is 555 in every 2 seconds, and therefore acceleration is constant. Please note the difference over here. Here the velocity is constant. The velocity is 555. Here the velocity is changing. The initial velocity and final velocity here are 0 and 5, here 5 and 10, 10 and 15. So the velocity is changing. What is remaining same is the change in velocity per unit time. So velocity is changing, but the change in velocity is 5 in every 2 seconds, and that is uniform acceleration. So this is an essential difference that you need to keep in mind between uniform velocity and uniform acceleration. Okay, if I plot a graph of v versus t, v versus t, this will give me change in velocity, and change in velocity is 5 every second. Right? What we'll get, we'll again get a straight line if you plot v versus t, because the change in velocity is constant per unit time. Here we have plotted s versus t. The change in displacement was 5 every time, 5, 5, 5, 5. Therefore we got here the change in velocity is same. So he'll get a straight line graph over here for vt graph. There's one more aspect that I want to cover when I'm talking of uniform acceleration is we have plotted a vt graph, and supposing we want to plot a st graph for this. So I'll have to calculate the distance covered by the body. Right? So what I'll do is I'll extend this table here, and what we will try to do is during the first 2 seconds, the velocity changed from 0 to 5. So in these 2 seconds, what was the average velocity of the vehicle or the object, right? So I'll have over here average velocity during these 2 seconds, 0 to 5. So 5 plus 0 by 2, so 2.5 meters per second, meter per second. In these 2 seconds, the velocity was 5 and 10. It was hovering between 5 and 10. It was increasing from 5 to 10. So what is the average velocity? 10 plus 15 upon 2, 15, 7.5. Here 15 plus 10, 25 by 2, 12.5 meters per second. And here this is 20 plus 5, 35, so 17.5 meters per second. So this is another important point about uniform acceleration. The average velocity, as you can see, is keeping on increasing. The velocity increases, average velocity also keeps on increasing. So what is the distance or displacement, distance covered? Okay. If I take average velocity and multiply it by the time, I'll get the distance covered. So 2.5 into 2 will give me 5. Okay. 7.5 into 2 would give me 15 meters. So in the first 2 seconds it would cover 5 meters. In the next 2 seconds it would cover 15 meters because its velocity is increasing from, or is between 5 to 10. Here the velocity was between 0 to 5. Here the velocity is between 5 to 10. So it covers more distance in these 2 seconds. In these 2 seconds it will still cover more distance because the velocity has now increased or is between 10 and 15. So 12.5 into 2 would give me 25 meters. And here 17.5 into 15 would give me 35 meters. So this is the distance covered and the cumulative distance. That means the distance from the origin Distance from the origin would be 5. Distance from the origin 5 plus 15. So 20, 45, 45 plus 35 would be 70, 80 meters. This would be the distance from the origin. So as you can see over here, the distance in every 2 seconds keeps on increasing. And therefore, if I plot a graph of S versus T, I'll get a very interesting graph, S versus T. T is between 0 to 8, so I can take this as 2, 4, 6 and 8 seconds. And distances I can put is between 5 to 80. So let us say I take, say, 20, 40, 60 and 80. I want approximate values, right? I'm not very keen on getting exact values because I just want to show you the nature of the graph. 30, 50 and 70. So in the first 2 seconds, right? Initially when it is at 0 second, the displacement was 0, so I can get this as the point. After 2 seconds, it has covered 5 meters. So after 2 seconds, the distance covered is 5. So I'll get a point somewhere over here. At the end of 4 seconds, it's at 20. So it is at 20. At the end of 6, it is at 45. So if I take 6, it would be somewhere over here. And at the end of seconds, it is at 80. So it is here. So these are the points that I have got, and the graph that I get is a curve like this. And these are the various points. Now compare the ST graph. Here in this case the ST graph was a straight line going up, whereas here the ST graph is a curve going up. The reason being here, in every fixed intervals of time, right, it was covering 5 meters, 10 or whatever, 5 meters every 10, 10 and 10 in every 2 seconds. So the distance covered was constant in every 2 seconds, whereas here in every 2 seconds it is covering more and more distance. In the first 2 seconds 5 meters, in the second 2 seconds 15 meters, 25 and 35 and so on and so forth. And therefore what is happening is in the same intervals of time, in this intervals of time it is covering this much distance, whereas in these 2 intervals of time it is covering this much distance. In these 2 intervals of time it is covering this much distance. In these 2 it is covering this distance. As you can see, this keeps on increasing. It was only this much over here, it has become this much over here, it has become this much over here and this. So it keeps on increasing because it is moving with uniform acceleration, meaning the velocity is increasing uniformly. Here is whereas here is velocity is constant. Okay, I think with these 2 examples and these two comparisons, you have got a good idea about the difference between uniform velocity and uniform acceleration. Thank you.